Simultaneous equations. First of all, let's look at solving the equation. There it is, 3x plus 5 equals 10. But what I want to do is to solve it by plotting the graph. So if we used some graph plotting software, we would plot 3x plus 5 equals y and look for the value of x when y equals 4. So we could solve graphically. We could plot the graph of y equals 3x plus 5, and then once we've got the graph, find where y equals 10. So that's, what did I put 4? No idea. So look for the value of x when y equals 10. Okay? So let's go to autograph and try that. So fire up autograph and put in the equation. Enter equation, y equals 3x plus 4, is it? That's 5. Well, I'm so obsessed with the number 4. And there is a line, okay? Maybe you would have expected a straight line because x is only linear power for x. It's not x squared or anything like that. So I was expecting a straight line. And we're after the point when y equals 4. So if we go back and look at the graph and zoom out, then it looks as though, coincidentally, no, when y equals 4, when y equals 10, here, I'm after the value of x. So when y equals 10, I want to know what x is down here. So I can use autograph nicely to zoom in on it. So I zoom in on it, and when y equals 10, x equals 1 point something. So I could zoom in again, and again when y equals 10, x equals about 1.66. So it looks like it's 1 2/3 or 1.66 recurring or something like that. So when y equals 10, x equals 1.666, something like that. Okay. So I could put this into autograph, into my notes rather, and that would be the value. So graphically, x equals 1.6 recurring, 1.66 recurring. Okay. Graphically, it's difficult to get an exact answer with these things because you need to zoom in. Algebraically, we get an exact answer. 3x plus 5 equals 10. How would I solve 3x plus 5 equals 10? Minus 5 from both sides. So 3x equals 5. And then divide by 3. So x equals 5 over 3, which is 1 2/3. And as a decimal, that's 1.6 recurring. Okay. So we can see that the exact answer is 1 2/3. The graphical estimation is 1.66 recurring, which is the decimal form. Okay. If I have another equation, if I have two equations and two unknowns, I can solve them simultaneously. Two unknowns and two equations I can solve simultaneously. Hence, simultaneous equations. X plus 5 is 10. 3x plus 5y equals 10. 2x minus 6y equals 12. Now, I have no idea what the solution to that is, or even if there is a solution. I've just made those figures up. Okay? So say you had an engineering situation and you ended up with two situations like this. X and Y could be the measurements of a certain thing or the cost of an item. So 3 lots of the cost of that item plus 5 lots of cost of that item comes to 10. 2x minus 6y equals 12. I have no idea what x and y are, just know that whatever they are the same in both equations. So whatever value x has in equation 1, it's the same in equation 2. So it's common to label in equations 1 and 2 like this. So one way would be to plot them graphically. So this time I would just literally plot this equation, 3x plus 5y equals 10. And then I would plot 2x minus 6y equals 12. And where they cross would be the point at which x and y have the same values in both equations. In other words, they would be the solutions. So if I look at the graphs, first of all I can see, is there a solution? And there will be if they cross. And secondly, I can find out what a solution is. So let's try that an autograph. So if we plot these two graphs, here they are, 3x plus 5y equals 10 and 2x minus 6y equals 12. They're crossing around here, so I know that there is a values for x and y that satisfy them. All I've got to do now is zoom on this part of the graph enough times to get a decent solution. And that's where it starts to get awkward, because the lines can start going together, autograph can start playing up, all sorts of things can happen. I want to zoom in on these points. I might want to stretch out the y-axis to get those points further apart, and then again zoom in. And it looks like x is around about 4.286 and y, so it looks like x is about 2.486 from this, going up, 4.286, 4.286, and y is around about here somewhere, negative 0.566. And they would be my values for x and y, not whole numbers by any stretch of the imagination. Okay, so I could always plot them graphically. And get my result. Oh yeah, 0.572, well spotted. I didn't read the scale properly, did I? About 0.572, something like that, just past the 0.57. So let's put this in the note. So we can solve graphically using some graph plotting software like Autograph. And there it is. We can also solve algebraically. And there's two techniques I want to look at. Either by elimination or substitution. No, I think so. Elimination or substitution are the two techniques. This is the more general, the more powerful, more general method. So let's try and solve these using these two techniques. First of all, by elimination. So solving by elimination. let's look at these two equations. The idea is to make either the x's or the y's the same so they can eliminate them by adding or subtracting the equations. That's the method. If I were to multiply, well, let's look at these numbers. I've got 3x in here and 2x in here. We look for a number that they both go into, common multiple, which is 6. 3 goes into 6 and so does 2. So I could multiply equation number 1 by 2. If I multiply everything in equation number 1 by 2, it's still true. So I'd end up with 6x plus 10y equals 20. Then I'd have 6x in this equation. If I multiply equation 2 by 3, I'd get 3 lots of 2x is 6x minus 18y equals 36. And I'd have 6x in both equations. And then I would subtract one equation from the other, and when I did that, the x's would disappear. Or I could think of a number that 5 and 6 go into, which would be 30. So times equation 1 by 6, and I'd get 30 lots of y. Equation 2 by 5, and I'd get 30 lots of y. Notice this time, though, that 1 is positive and 1 is negative, so to eliminate, I'd add them, because I'd have plus 30y and minus 30y, so if I added them together, they'd be eliminated. So I've got choices, okay? You look at it and decide which way is going to work most easily and conveniently for you. Probably I would try and get the x's the same, because that would involve smaller numbers. I've only got to times by 2 and 3. So what I do is I say, okay, I'm going to multiply equation 1 by 2. So shorthand way of writing that, equation 1 multiplied by 2. And I get 6x plus 10y equals 20. Now I've got a new equation, so let's just call that equation number 3. What I'm going to do with equation 2? Multiply it by 3. Right. So you do that. 3 lots of 2x is 6x. 3 lots of minus 6y is minus 18y equals 36. Call that equation 4. Again, I've got a choice. I'm either going to do equation 3, take away equation 4, or I'm going to do equation 4, take away equation 3. Either way, the 6x's are going to disappear. But choose a way that's going to be convenient. So if we look at this for a minute, if I do equation 3, so that's 10y, minus equation 4, I'm going to get 10y minus minus gives me a plus 18y. So I'd end up with 28y. Positive. That's good. If I do it the other way, 4 take away 3, I'm going to have minus 18y minus 10y is minus 28y. Negative, not so good. So try and do the subtraction so that you end up with a positive number of y's. That will make life easier for yourself. So I'm going to look at this and say, right, it's more convenient to do equation 3, take away equation 4. So I end up with positive y's. So then I get 10y, 6x is minus 6x, that's gone, that's the whole point. 10y minus minus 18y is 28y equals 20 minus 36 is minus 16. Divide by 28, y equals minus 16 over 28, which is somebody? 0. Right, blah blah, we can round it, okay? 0.5714. If we want an exact answer, we could leave it as a fraction. What's that? That's 8 over 14 or 4 over 7. So that's actually negative 4/7 to be exact. So this is an exact answer. So the algebra gives me an exact answer, exactly. If I want it as a decimal, negative 0.5714. Don't forget the negative. And if we compare that with our graphical solution, negative 0.57 we got for y. So this way we got negative 0.5714, or exactly minus 4 over 7. So the algebraic technique gives us a more exact answer. Now we've got one equation, or one value rather, what y is. We can substitute that value for y back into one of the original equations. We now know y. Y is minus 4 over 7 to be exact, so let's leave it like that. So instead of y in equation 1, I'm going to write minus 4 over 7. So what I would do is I'd say substitute into equation 1. And so I'll rewrite equation 1, 3x plus 5y, but what's y is minus 4 over 7 equals 10. Get it right this time. So I've substituted in my value for y into equation 1. Now I can work out what that is. 3x, 5 4s are 20, so it's minus 20 over 7 equals 10. Now what I'll do to get x? Oh yeah, I can see why you're doing that, to try and get rid of that 7 that's underneath. Yeah, we can do that. So multiplied by 7, we get 7 3s are 21x minus 20 equals 10. Excellent. Next. Add 20 to both sides to get rid of the 20. 21x equals 30. And finally, divide by 21. Exactly, 30 over 21. Didn't I do that? Yes, I did. 20 over 7 times 7, they cancel. That's why we did it. So times that by 7 to get 21, and times that by 7 to get just 20. And that by 7. Oh, well spotted, Tom. Yeah, that should be a 70. So in fact, this is... let's think about this. Times both sides by 7 minus 20 equals 70. Add 20 to both sides, so that becomes 90. So in fact, it's 90 over 21. Well done, yeah. Exactly. I'm rushing, which is not good. Okay? So now I've got an exact answer, but if I want that as a decimal, what is that as a decimal? To 3 significant figures, say. So if I want it as a decimal, 4.29, and if we compare that with our graphical method, 4.286, we got it. So we've got a decimal answer, but also an exact answer algebraically. Okay, so let's just review that quickly, this method, because this is the elimination method. So let's look at it. There are two equations. Solving by elimination. Think about what you're going to multiply these equations by to make either x's or y's the same. So just a bit of thought goes in to start off with. How am I going to make either the x's the same or the y's the same in the original equation. We've chosen to try and make x's the same by multiplying equation 1 by 2 to get this, and equation 2 by 3 to get this. So now the x's are the same. We can eliminate by subtracting in this case. But sometimes if one's positive and one's negative, you don't subtract, you add to eliminate. Okay? So we eliminated the x and then calculated y, we can get an exact answer. Once we've got that answer, we substitute back into one of the original equations and calculate y. Okay? Now, if this was an exact an engineering example, and you really needed to know you'd done that right, at the end, you would check. You've got no one there on site to check that that's done correctly for you. You know, you don't want to do that. You're the guy in charge. You've got to work it out. You need these values of x and y, and so you check. You check in the original equation that you didn't use in the first place. So I substituted into 1 to get the other value. I check in 2. In other words, I rewrite equation 2, which is 2x minus 6y equals 12. And then I put in what I think x is and what I think y is and see if it works. So x is 4.29, or 90 over 21. So 2 times 90 over 21 minus 6 times y, which is minus 7 over 4, should equal 12, if we're right. Go with the exact answers and we'll get it exactly right. 2 times 90 is 180 over 21 minus a minus gives us a plus. 6 is 36, 42 over 4 equals 12. And if you want to just check that on your calculator, you should find that that works. It doesn't come out right, so that's a good job we checked. So let's have a look and see if we can see where we went wrong. I actually inverted the 7 over 4, so it should have been minus 4 over 7. So 6 4s are 24, so that's plus 24 over 7, not. And now it comes out, hopefully. Yeah. So that highlights, doesn't it? You know, that's why I did that, so that we could spot just how important it is to check. Little deliberate mistake there. So to solve by substitution, the idea here is it involves more algebraic steps, so it involves more confidence with algebra. What you do is you take either equation 1 or equation 2 and look at it, and then think which is the easiest one to rearrange to read either x equals something or y equals something. So I'm going to try and rearrange equation 1, say, to read x equals something or y equals something. And then in the other equation, equation 2, I'm going to substitute in that expression for either x or y. That's the plan. So let me show you what I mean by that. I'm going to rearrange equation 1, say for x. It doesn't matter which way I do it, okay? So let's do that. Rearrange one for x. These are quite straightforward equations, so actually it's just as easy to rearrange for x as it is for y. So I had no decision to make as to which is the easiest to rearrange, because they're both fairly straightforward linear equations. That means I rewrite equation 1 to say x equals something. So I want to get x on its own. So 3x plus 5y equals 10. I'm after getting x on its own. So what would be the first thing to do? Divide, you mean to get, yes, but before we do that, because I've got to divide every term, subtract the 5y. But you are right. Let's subtract 5y from both sides. 3x equals 10 minus 5y. And now divide by 3, okay? And then x equals 10 minus 5y all divided by 3. So we've rearranged equation 1 to read x equals 10 minus 5y all divided by 3. Now substitute this expression here, for x into equation 2 and solve it. So in equation 2, instead of writing x, or wherever x appears in the equation, we substitute that expression. So 2 times that expression, 10 minus 5y over 3 minus 6y equals 12. Now we've only got one unknown, y, and so we should be able to solve it. It's very like the sort of equations you were doing last week. So Alfie, all divided by 3, so you like to multiply 3 by 3, good step, okay? That's probably what you're going to say. Multiply everything by 3 to get rid of that 3 underneath. So that means 2 times 10 minus 5y minus 18y equals 36. So I multiply every term by 3. And then what? Next thing probably would be to multiply out the brackets. So what would I get? Multiply out the brackets. 20 minus 10y minus 18y equals 36. Now look at the left hand side. Can we simplify it? Minus 10y minus 18y is no 28y minus 10 minus 18 minus yep. So I can collect together the like terms. Then one of the little tricks at the start, if the thing you're trying to get is negative, add it to both sides. 20 equals 36 plus 28y, Alex. Add 28y to both sides. Yeah. Then subtract 36 from both sides. So minus 16 equals 28y. Then divide by 28. So minus 16 over 28 equals y. Therefore, y equals minus 4 over 7. Exactly the same answer as we had before. So now, as before, substitute y into number 1 as before to find x, then check in 2. So it's the same as the elimination method. So first job with something like this is there a solution? So plot it, okay, on autograph. So if we plot it graphically, we can see there's no solution. There's no value of x and y that satisfies these two equations because the lines do not cross. Okay, so you can't do it. So it's well worth plotting because there's not always a solution. So in this case, no solution. Okay. Let's try another example. So in this example 2 here, where we just changed the 10 to a positive 10, we find that now the lines do cross, so we do have a solution. In fact, there are 2 possible solutions. So let's go through that and see why. The reason why there are 2 solutions, as we'll see, is because at some point to get x, there's a square in there. And when you square root a number, there's two possible answers. It could be positive or negative when you find the square root. And that's what's going to lead us to having two solutions. So let's have a look and see. The elimination method is not so straightforward now because we've got, well, y's and x's not the same. We can try the elimination method and try and eliminate the y's and solve x. We can do that. Or we can try the substitution method, okay, to solve it. So let's try substitution, the more general method, and get into the algebra, shall we? And then you can try the elimination yourself and see if you can get that to work by making the y's the same. So let's look at the substitution method. So let's take these two and have a go at them. So by substitution, solve by substitution. And what I'm going to do is rearrange equation 1 to get y on its own. Or equation 2. Actually look at that one. It's plus 10y, so let's rearrange 2 for y. Because that looks like the easiest one to do. So I want it to lead y equals something. Have a go. So y equals 10 minus 8x all divided by 10. Now substitute this into equation 1 and solve. So we get, substituting into 1 and solve, trying to solve, substituting into 1. So instead of y, we write the expression 10 minus 8x over 10. Now we try and solve it. What are you going to try and get rid of first, Alfie? Multiply every term by 10. 10 threes are 30. Minus 4 brackets 10 minus 8x equals 20. Same sort of things all the time that we do. Because this expression, why do we not times? Because if I times this by 10, the 10's cancel, and I'm just left with the... Yeah. Yes, that's right. So by multiplying by 10, I'm getting rid of the divide by 10 bit, so that's why I'm left with just the top bit. That's why we did it, Alex, okay? To get rid of that 10 underneath. What would you do now? Hang on, what would you do now? Get rid of the brackets, yeah. So,
split, for example, 2y, would that become 4y or would it become 4y squared?
if you squared the expression 2y, you get 4y squared. Yeah. So, multiplying out the brackets, 30x squared minus 4 times 10 is minus 40. And watch this bit. Minus 4 times minus 8 is plus 32x. So be careful of that double negative when you're multiplying out brackets. Now, this is a quadratic. So we need to be able to solve quadratic equations to go on from there, which I'm sure at some point you've all done something on it, but it's a little while maybe, and that's what I want to look at, okay? Before we do that though, I want to just give you a chance to have a go at practicing some of these simultaneous equations. So we'll pause there for now and then come back to this question and finish this one off.